So starting off with the very first process of cellular respiration is glycolysis. Now glycolysis is one of the only reactions, or the only processes that can begin without oxygen. So oxygen is not needed in order to kickstart this reaction. So the real question is, what starts glycolysis? Well, simply, 2 ATP starts glycolysis. From there, this whole reaction, whole glucose molecule breaks down into NAD+, as well as 2 ATP breaking out of it at the very end. Now, if you combine this NAD+ with a hydrogen molecule, you're going to get yielded NADH, which is an electron carrier that is going to be later used in future reactions. Now, glycolysis is repeated twice. So, same thing here. Put a hydrogen here, and you're yielded out NADH, as well as 2 more ATP being yielded. In the very, very end of glycolysis, you're going to be ended up with 2 pyruvates as well, since the glycolysis is broken down into pyruvates. And in case you guys don't know what pyruvates are just molecules that are made with 3 carbons. So glycolysis has 6 carbons. Pyruvates is broken down into 3 carbons each. So, the very, very end of glycolysis involves 2 pyruvates, 2 net ATP, since don't forget, 2 was used to start the whole thing up, and last but not least, 2 NADHs.
Oh, what the hell? My God, no.
Glycolysis is an anaerobic process, which means that it does not require oxygen to function. If there's still a lack of oxygen, then fermentation occurs, which is another anaerobic process. But in the presence of oxygen, pyruvate oxidation and the rest of the cellular respiration processes occur. The other cellular respiration processes are aerobic, which means that they require oxygen to function. In bacteria, you get alcohol fermentation, and this is when the 2 pyruvates from glycolysis enter the reaction and they lose 2 carbon dioxides, which get expelled. The pyruvates then convert into acetaldehydes, and the 2 acetaldehydes then react with 2 NADHs from glycolysis and turn into ethanols. And the NADHs convert into NAD after losing their hydrogen. The NADs then return back to glycolysis to restart the glycolysis reaction.
Shimmy, yeah, shimmy, yeah, shimmy, yeah. Drink. La 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 la. Drink.
Fermentation is an anaerobic process, which means that it does not require oxygen to happen. And in humans, you have lactic acid fermentation. In lactic acid fermentation, the 2 pyruvates from glycolysis react with 2 NADHs to become 2 lactates, and the NADHs lose their hydrogen and become NADs. The NADs then return back to glycolysis to be reused again for the glycolysis process, creating more ATP. The lactates then wait until there's oxygen present in the body to become pyruvates again.
Our next process is pyruvate oxidation. And this is just a prep up for what's going to happen in the Krebs cycle. So, we break down this pyruvate into coenzyme A. Now, in the process of coenzyme A breaking down, we also have NAD+ being broken down again. So, like same process as glycolysis, add a hydrogen there, you're going to get NADH. However, if you add 5 hydrogens, 1, 2, 3, 4, 5 hydrogens to coenzyme A, you're going to be yielded acetyl coenzyme A, CoA, as well as 1 carbon dioxide being given off. Now, keep in mind, this whole reaction repeats twice. So this whole thing is going to be repeated over and over again with a net yielding of 2 acetyl CoAs, 2 carbon dioxides, and 2 NADHs.
Legalize nuclear bombs.
Okay, so after pyruvate oxidation comes the Krebs cycle. It's going to start off with one acetyl-CoA. The acetyl-CoA is going to break down to a coenzyme A as well as a citrate. Now, what's funny about the citrate is this. There's going to be a few NAD pluses to H transitions here. So the first NAD plus and H transition. This citrate, right there, you're going to take a carbon, and that's going to yield together an NADH and a CO2. The same process is repeated here. So NADH and H plus the citrate, the 2 carbon at least, because these two take 2 carbons total. That's going to go away. Now we have NADH and CO2. Now this is a little funny one right here. We're going to have GDP combine up with a phosphate group. Now this together is going to give off GTP. Now there's a reason why I have 2 white pieces of paper right here, because this represents 1/2 of the Krebs cycle, and this is the second half. And in case you guys are wondering what GTP is, it's almost identical to ATP. Just the base, so instead of adenine, there's a different base. Now, after that half, to start the second half of the Krebs cycle, FAD is going to come into play. Now, FAD is going to combine with 2 hydrogens. That's going to go away. And FADH2 sub 2 is going to be coming into play. Now, FADH sub 2 is really just another electron carrier. It's almost identical to how NADH operates, just the same thing. Now, after that FADH2 conversion, we're going to have our third and final NAD plus to H conversion. Now, what's special here is that no carbon is taken away from this whole thing. This citrate right here flows on throughout the entire cycle, but no carbon is taken there. That's going to yield us an NAD plus again. Now, we have a leftover 4 carbon molecule, because keep in mind, only 2 were used throughout the entire cycle. This 4 carbon molecule is called oxaloacetate. This oxaloacetate is then going to be used to combine with this CoA, which is going to equal out to 6 carbons, which is going to give us back acetyl-CoA. Now, keep in mind, every single product from this Krebs cycle is multiplied by 2, because there is simultaneously 2 different Krebs cycles going on. It's not repeated twice, it's just going on twice.
I wish I knew you wanted me. I wish I knew. I wish I knew you wanted me.
In the electron transport train, you have 10 NADH and 2 FADH to start off with, along with 6 oxygens. The NADH and the FADH react with proteins on the inner membrane, losing a hydrogen and turning into NAD and FAD. The 6 oxygens then react with the hydrogens and create 6 H2Os. The 6 H2Os then get expelled, and the remaining hydrogen become hydrogen ions. The hydrogen ions are positively charged because they lose an electron, and now there are more protons than electrons in the atom. The hydrogen ions then enter the space in between the inner and outer membranes of the mitochondria, and the electrons enter the inner space of the mitochondria. This process continues until there is a hydrogen gradient, where there are many positively charged hydrogen ions in the inner space and many negatively charged electrons on the inside space. Then, as soon as this gradient is reached, a process called chemiosmosis occurs, where hydrogen ions flow through ATP synthase, causing the ATP synthase to activate. And as the hydrogen ions activate the ATP synthase, ADP converts into ATP through a process called substrate level phosphorylation. That process occurs until there are 34 ATPs at the end.
Thought you were too good for me, my dear. Never gave me time of day, my dear. It's okay, things happen for reasons that I think are sure. Yeah, I wish I